Okay, so let's get started. So this class, we're going to talk about the aerosol size distribution measurement. Before we do that, let's do a quick recap of our last class. So last class, we mainly introduced the methods for aerosol mass concentration measurements. So we introduced the filter sampling, the criteria where we select different types of filters, and then we briefly introduced the impactor or cascade impactor for measuring the aerosol mass-based size distributions. We're going to come back to the impactor measurement later on. Then we introduced the beta attenuation monitor, the TEOM, the CPMA, and the OCEC analyzer. So all of these measurements will provide you the mass concentrations of the aerosols. Okay, so this class we're going to talk about the aerosol size distribution measurements. So similar to the question that we asked when we introduced the aerosol number concentration measurements or the mass concentration measurement, now we have a new question. So why is the size distribution so important? Why do we have to do such measurements? All right, so if we recall, when we introduced the aerosol number concentrations, we said that the aerosols are of different sizes, and different sized aerosols, they may have different toxicity, right? So that's related to the health effects. And in terms of the ambient effects or the atmospheric system, aerosols of different sizes are produced by different mechanisms. We also covered this briefly in our introduction class. We said that there are different modes of aerosols: nucleation mode, Aiken mode, accumulation mode, and course mode. And each of these modes are generated or they're consumed due to different mechanisms. So to better understand the physical and chemical processes that's happening in our Earth's atmosphere, and further to predict the climate effect, we need to know what is the concentration of aerosols in different modes, or to understand their size distributions. So this class, or for the next few classes, we're going to focus on the scanning mobility particle sizer, or people also call it as the size distribution mobility, or call it the SMPS. So depending on the mechanism, there are also instruments called the DMPS, right? So basically, it's based on the operating condition of the system, but they use the same working principles, right? So the scanning mobility particle sizer, or the DMPS, are the most widely used instrument to monitor the aerosol size distributions. Excuse me. Especially use these instruments to monitor aerosols with sizes below 1,000 nanometer or submicron aerosols. Okay, so submicron aerosols are very important because they occupy, or they dominate the number concentration of aerosols that's suspending in our air. The particles of larger sizes, they just settle down more easily or get impacted or get lost more easily. But for these submicron aerosols, they can suspend in the air for a long time. So here I'm showing you a few pictures of the SMPS systems. So these systems can be from the same company, right? So for example, these two are from the TSI. They represent the newer version that's showing here, or the older version that's showing here. And some SMPS systems, also some SMPS systems from other companies. So by directly looking at these different pictures, of course, their appearance can be very different, but there are some commonalities, right? So are there anything in common? So you can see that there's always something like a cylinder sitting in between two instruments, right? And you also have a box on the left and box on the right. So for this one, this might look familiar to you, right? This is a CPC. This counts the aerosol number concentration, right? So the unknown parts are actually this box, where we call them electrostatic classifier, and the column here. And the column is called the differential mobility analyzer. And then, of course, we have this CPC here. So basically, the SMPS system is composed of a electrostatic classifier. People also call it as EC, plus a differential mobility analyzer. People call it as DMA, plus a CPC. Okay, so the SMPS is composed of these three parts here. So this class we're going to basically talk about the EC and DMA, especially the DMA. So the DMA is used for basically selecting particles of different sizes. So if you zoom in or to try to look at the schematic diagram of the EC and the DMA, so basically you can see there are many tubes here, right? There's also inlet, there's also outlet. So the outlet of the DMA goes to the CPC, right? So if you look at the internal structure of the SMPS, this is how it works. So we introduce the aerosols from this inlet here. So the aerosols will first go through an inlet impactor. This is to remove the aerosols of larger sizes, right? Sometimes you don't want to measure particles about 1 micrometer or even 500 nanometer, right? To just focus on certain size ranges. You could use different sized impactors to get rid of the larger particles. And then these aerosols will be introduced what we call a neutralizer, okay? So what the neutralizer does is it gives the aerosols a uniform or a known charge distribution. So what it means is that, for example, if you have 100 particles of, let's say, 100 nanometer, right? So neutralizer, what it does is that it releases bipolar ions, right? So it releases bipolar ions, and then they will collide with the particles that's being introduced into the neutralizer. So because of the charge, this steady state charge process, right? I would say steady state diffusion charging. So the number of charges that's basically eventually carried by these particles are fixed. So there will be certain percentage, let's say F1 of particles carrying +1, certain percentage of 2 carrying +2, F-1 carrying -1 charge, F-2 carrying -2 charges. And then there's also a fraction of particles carrying 0 charges, right? So what the neutralizer does is that it neutralizes the ions on the particles so that they carry let's say a constant charge distribution. So these charges are the same. So we use the neutralizer in the case or in the scenario, for example, the aerosols are uncharged at the beginning, and then they're being introduced to the system. So neutralizer give charge to these aerosols, so they are carrying a uniform charge distribution. It also happens if we have the particles of if all of them are charged, right? For example, there can be scenarios that you provide a lot of the same polarity charge onto the particles. And once they're introduced to the system, the neutralizer will redistribute the charge onto these aerosols. So they're still having this, this uniform charge distribution here, right? So sometimes people will also call the neutralizer as the charge conditioner. So basically, it preconditions the charges onto the particles so that we know what is a fraction of particles carrying certain charges. Okay, so after the neutralizer, the aerosols or the charged aerosols or charge conditioned aerosols will be introduced into the DMA here. As we see earlier, the DMA is made of these cylinders. But inside the cylinders, actually there are 2 cylinders. There are 2 concentric cylinders. Right, so you can have the outer cylinder, which is grounded, right? It doesn't have any charge. Otherwise, if it has high voltage, then it's going to shock people, right? And you also have the inner cylinder. And the inner cylinder is connected to the high voltage, okay? So the aerosols are being introduced into the, let's say, the upstream of the DMA, and then it's going to get redistributed through this structure here. Actually, it may look like it's entering from the side or left to entering from the left side or the right side. Actually, it's redistributed, or the flow is distributed through a inlet ring. Okay, so on the inlet ring, there are different inlets, right? Multiple inlets, where you can introduce the aerosols more uniformly. So the aerosols are introduced into the gap between these 2 cylinders, and because of the electrostatic charge, they will move due to the let's say the migration velocity, right? The electrostatic force. So some particles will get selected and then they will exit from the outlet here and then introduced into a CPC. Okay, so this is how the aerosol flow works. You can see that here, basically this thinner tube is going to the aerosol inlet, right? You can see that here very clearly. But you see that there is also a wider tube. So what does the wider tube work? And what is that flow? So we introduced that the aerosol, we talked that the aerosols are being introduced to the gap between these two cylinders, but they move not because of gravity, because for the submicron particles, their gravity is too low. They move too slow, right? So what happens is that we introduce a flow that's called the sheath flow, or we call it sheath air. So the sheath air, which is the main flow going through this gap between these two cylinders, will basically bring these particles due to the drag force and quickly let the particles to flow with the same velocity as the sheath air. And then this sheath air will provide the flow or provide the velocity of the particles vertically, right? At the same time, the electrostatic force is going to be applied onto the particles so they can move horizontally. Okay. So if you look at the flow of the sheath air, you can see that it's being introduced from the inlet on the above, going through this gap between these two cylinders. They need a flow straightener. Basically, it's a screen here to redistribute the velocity so you don't have the non-uniform distribution of the flow profile, right? And then if you follow, the sheath air is being introduced or marked as the green as the blue line here. Right, so the sheath air will exit from the bottom and then being withdrawn. Okay, so you can see the excess sheath air will first go through a particle filter, so to get rid of the particles, because you don't want to introduce any particles into the system, right? You only want to introduce the aerosols into the system through this aerosol line. So it's being cleaned up in the particles, and then it will go to a sheath pump. So the pump will withdraw the flow from the outlet of the DMA so that the sheath flow will go out. And then since the pump itself can generate some particles due to the lubricate oil, right? So you need another filter to get rid of the particles, and then you need a heat exchanger since the pump generates heat itself, right? And then there will be temperature sensors, flow meters, basically flow sensors, RH meters to make sure that relative humidity is in the appropriate range, right? And then go to a pressure sensor and then send the cleaned sheath flow back into the inlet of the DMA or the sheath inlet of the DMA. So basically this sheath air here is conserved, right? So you have the sheath in equals sheath out. And if you look at the inlet and the outlet of the DMA, you only have four ports, right? So you have two inlets, right? The sheath inlet, the aerosol inlet. You have two outlets. That's the CPC or the aerosol outlet and the sheath outlet. So if we're making sure that the sheath inlet and the sheath outlet are having the same flow rate, then it means that the aerosol inlet and the aerosol outlet are having the same flow rate. Since we mentioned that the CPC normally has the internal pump, right, to pull certain flow rate, or you need the vacuum source to pull the aerosols. So this means that the DMA or the whole electrostatic classifier or the SMPS, the flow rate here, let's call it QA here, aerosol flow, is just going to be determined by the flow rate that's withdrawn by the CPC. Let's call it QS, Q sample. Okay, so because of that, you don't need any inlet pressure to push the aerosols inside. So the CPC will withdraw the flow, and since the sheath flow is balanced, so it's going to withdraw the flow from here, and then eventually withdraw the flow from the outside, right? So this is how the flow diagram or the flow system works. And also you can see here we have the high voltage power supply to provide voltage to the inner electrode so that you can basically control the voltage that's being applied onto the DMA. So this is showing the schematic diagram of a SMPS system using classifier and a lone DMA. The lone DMA is, as the name means, right? So you have a relatively long dimension, and I would say it's close to maybe half a meter, right, or around maybe 40 centimeters. So there are also different geometries of the DMA. So here is showing a nano DMA, or this is a newer version of the DMA called 1 nanometer DMA. This is to monitor aerosols with even smaller sizes, right? So for these DMAs, to reduce the diffusion, as we introduced earlier, if you want to reduce the diffusion, since we're trying to measure these 1 nanometer particles, their diffusion coefficient can't be changed. So one thing you have to do is to reduce the time. So if you want to reduce the time, you need to reduce the total dimension of the length of the DMA, right? So in this case, the particles travel for a shorter time, and then you can reduce the diffusion, the Brownian diffusion effect onto the particle size selection. Okay, so these are showing the schematic diagram of the DMA. And as I've introduced earlier, there are different dimensions, like the TSI long DMA is relatively long, it's around 44 centimeter, and the nano DMA has a dimension of around 5 centimeters. And this is just showing the internal diagram of the DMA again. You have the aerosol in, right, from the top, and people normally use a QA as the to represent the flow rate of the aerosols introduced into the DMA. You also have the sheath flow that is called the QSH, right? So then at the outlet, so you have the classified aerosols or the aerosols exiting through this outlet here, and we call that as the, oh, not that one. Aerosols exiting, we call them as the QS, right? So Q sample. That's going to the CPC. And then there's also excess of the sheath flow, because sheath flow, we said, is the main flow that's going through the DMA. So the excess of the sheath flow is just called the QE, right? So because of the flow balance, we can set up the equation that QA plus QSH, Q sheath, equals QE exhaust plus Q sample, right? So we're going to talk about these different flow rates when we further derive the working principles of the DMA or of the SMPS. Okay, so if we just go through this SMPS working diagram again, so we can have a stream of the ambient aerosols being withdrawn by the SMPS. We said that eventually it's a CPC that's withdrawing the flow, right? So it's being withdrawn into the SMPS, and then we will introduce them into a charge neutralizer. So I would say for most of the current SMPS system that we use, we normally will use these radioactive neutralizers. Because these radioactive neutralizers, they can just emit, let's say, different radiations to ionize the air that's in this neutralizer. Because we said that to neutralize the particles, we need to generate ions, right, to redistribute the charge onto these particles. So we use these polonium or krypton sources so that they can emit the air. They can emit either beta or alpha radiation. So they can ionize the air in the neutralizer, and then the ions generated will redistribute the charges onto the particles. Okay, so currently there are also newer, or I would say, new methods that try to avoid these neutralizers, because if you consider doing these measurements, let's say if you're doing that in the lab, then that's okay because the source is contained, right? But if you want to conduct these measurements in closely confined environments, or for example in hospitals or in the aircraft cabins, then because of the vibration, or people may be concerned about their safety, right? Although for these sources they are closely enclosed into these let's say these boxes or these cylinders, right? But you never know if there are physical damages. For example, you drop it onto the floor, then some of these radioactive materials can be released, right? And you're subject to some high radiation. So because of that, there are some newer works that are talking about let's say, what about we don't use these radioactive materials, but use some other ionization methods? So there can be soft X-ray methods, right? So for the soft X-ray methods, it's still generating the ionizing species. So it's ionizing the air and then further charged particles. But there are even newer methods or newer algorithms that just try to use the ions in ambient air. So as we know, there are always ions being generated on our Earth's atmosphere. It can be, in our Earth's atmosphere, it can be from the solar radiation, or it can be the radon. That's just the ionization source in different construction materials. So these ionization sources can generate ions by themselves, right? So there's always some ions in our air, and then they can charge these aerosols. So if you just take the ambient aerosols, there's always certain fraction particles getting charged. So then the issue is that we want to make sure that the ions are conditioned, and we want to make sure they are a known condition, right? So for the radioactive materials, let's say for the polonium or krypton or soft X-ray, there are known charge conditions. There are equations to establish how many of these particles are being charged with certain charging state. For example, as we said earlier, there are experiments or there are established data about what is the fraction of particles carrying different charges or being neutral. But then for the ambient ions, we don't really know that, because the ambient ions really depends on the solar radiation or the radioactive materials that's in our construction materials. So there needs to be a way to back calculate what is the charge distribution and then further calculate what is the real size distribution of the particles. And I think Dr. Jian at Tsinghua University has really developed a lot of work on this area, and he has several webinars or talks regarding this method. Okay, so now let's still get back to the most common way to measure or to charge the aerosols. Let's say that we just use a polonium or krypton sources here, right? So they can charge the aerosols into a known condition, right? So after they're being introduced into the DMA, so here this is just drawing a half of DMA, right? So this is the, let's say, the center of the DMA, right? So this is the inner electrode. Let's assume it has a diameter of R1, and the outer electrode has a diameter of R2, right? So further, let's assume that the inner electrode is connected to a negative high voltage, right? If it's a negative high voltage, then the positively charged particles will get attracted, right? So then if we assume, let's just currently assume that particles are all singly charged, right? If they are positively charged, they're all singly charged. If let's just assume so, right? So if you assume that they are singly charged, then let's compare the movement of a small particle and a large particle. So no matter whether they are small or large, their force, the force that's added onto the particle is just QE. And further, the Q is a charge onto the particle, is further related to the number of charges multiplied by the elementary charge multiplied by E. But in this case, since they're singly charged, then their N is just 1, right? So it's just going to be this EE here, right? So the same thing for the large particles. So this is the electrostatic force. And then the electrostatic force is trying to pull the particles towards the inner electrode, right? So then because there's air here, right, in the horizontal direction, there's going to be another force since the particles are moving against the flow, right? Before the sheath flow, there's no horizontal direction of the flow. And then to counterbalance this electrostatic force, there will be a drag force that's pulling these particles, right, to counteract these forces. So if we set up the equation, then we're going to have EE equals 3 pi mu dP divided by C multiplied by V. Let's just name it VR, right? So you can see that basically we can calculate what is the horizontal velocity or the radial velocity. The radial velocity is just EE divided by 3 pi mu dp and then multiplied by c. So further, we said that c is proportional to 1 over dp in the free molecular regime, and c equals 1 in the continuum regime. Okay, so overall, you can see that no matter whether it's 1 over dp, proportional to 1 over dp, or equals 1, you can see that when the particle size increase, then you're going to have a smaller horizontal velocity. When the particle size decrease, you're going to have a larger horizontal velocity. So this means that the smaller particles are going to move faster compared to the larger particles. That's due to the balance between the drag force and the electrostatic force. And at the same time, we said that the sheath flow are actually giving these particles a vertical velocity, right? Since we're talking about submicron particles. One thing we know for these submicron particles is that they have a very short relaxation time. So what that means is that when you introduce the aerosols into a flow field, they will rapidly follow the flow, right? They will just basically suspend in the flow, right? So you can see that even for 1 micrometer particle, they just have a relaxation time of 3.6 multiplied by 10 to the minus 6 seconds. So what this means is that when we introduce these aerosols generally into the gap between these two cylinders in the with a velocity of, let's say, 1 meter per second, even at 1 meter per second of the velocity, then they can only move 3.6 multiplied by 10 to the minus 6 meters, which is 3.6 micrometers. And compare this distance, or this stopping distance, to the dimension of the DMA, which are in millimeters or in centimeters. The stopping distance is negligible. So this means that when we introduce the submicron particles into the DMA, or into the gap between these two cylinders, they will just follow the flow in the vertical direction. They will carry the same vertical velocity, right? No matter whether they're small particles or large particles. So because of that, you can see that in the vertical direction, they have the same velocity, but in the horizontal direction, they have different velocity due to their size. And smaller particles move faster, large particles move slower. And this means that when you apply certain voltage onto the DMA, only particles with certain sizes can get selected, right? And this is assuming that the particles carry one charge only. And if you have two charges, right? So the velocity, since we had an n here, the velocity here will be faster, right? Which means the larger particles carrying two charges can also move faster compared to the smaller particles. So there will be some even larger particles carrying two charges getting selected. But no matter which size they are, right, their electrical mobility is the same. So remember, the electrical mobility is this VR normalized by E, right? So that's basically NEC divided by 3 pi mu dp. So the particles that can get selected, they will have the same horizontal velocity, right? So because of that, particles are getting selected when they're having same electrical mobility, or when they're having the specific electrical mobility. Okay, so this is how we select particles with different mobilities using the DMA. And then the particles with uniform mobility, or let's say if they have the same charge, same number of charge, then they will have the same size, then they will be sent into the CPC to be counted with concentration, right? And further, for the scanning mobility particle sizer, what happens is that it will scan the voltage added onto the DMA. So if you scan the voltage, right, make it larger and larger, right, then you are going to select from the smaller size to the larger size. And then from the small size to the large size, then you can also get the number concentration. You can get the concentration that's monitored by the CPC, right? So to get a size distribution that you want. Okay, so this is a working principle of the scanning mobility particle sizer. So basically, it's using the electrostatic force to separate particles of different mobilities, right? And then by adding a scanning voltage, you can select particles of different mobility and then monitor their concentration. So then this is a working principle, but how do we convert the measurement into real size distributions, right? So if you think about what we control, how we control the SMPS. So basically, we give it a certain flow rate, right? Fix the flow rate, and then we change the voltage. And we said that different voltage will correspond to different electrical mobility, and then further correspond to different particle sizes, right? At the same time, the CPC will count a number concentration of particles with the same mobility, right? And to convert these controls or signals to the size distribution, there needs to be some calculations because this is not the real size distribution, right? So because right now you only have the voltage, you don't have the particle size, and also you have a CPC signal. You have a CPC signal that corresponds to particles with the same electrical mobility. There can be larger particles carrying multiple charges, and there can be smaller particles carrying a single charge. So how do we convert these signals to the size distributions? This is a two-step process, right? So first, we need to convert the DMA voltage to particle size. And the second step is to convert the CPC reading to concentration or to size distribution. So we'll talk about the DMA voltage to size conversion first. So basically, this conversion is bridged. Let's say you have voltage, you want to convert it into particle size. It's bridged through the electrical mobility, right? Because we said that at certain voltage, only particles with certain electrical mobility are getting collected. And further, the electrical mobility is related to the particle size. Okay, so we introduced earlier, right? So there's a correspondence between the electrical mobility and particle size that is just set by equating the drag force with the electrostatic force. QE equals 3 pi mu dp divided by c multiplied by v. This is VR, right? We can also call it radial velocity, right? The horizontal velocity. So VR equals QEC divided by 3 pi mu dp. And further, we said that the electrical mobility is related to the velocity by just normalizing it by the field strength, which is QC divided by 3 pi mu dp. Okay, so you can see here that the electrical mobility is related to particle size, but further, there is this Q here, which is the number of charge onto the particle, which means that for small particles, if they carry single charge, they may have the same velocity compared to a larger particle carrying two charges, right? So if Q doubles, then particle size can also double. So here, I also need to mention that the C is also dependent on particle size, right? So there isn't a one-to-one relationship. I would say basically there isn't a proportional relationship between the charge and the particle size. If you're talking about particles above 1 micron, there may be, because you can just assume that the C is 1, right? It's just a constant. So if you have a double charge onto the particle, then the particle size will also double, right? And to make sure that they have the same electrical mobility. But when the particle size is smaller than 1 micron, then we need to consider a more complex relationship, right? So we got this Z conversion to dP solved. Okay, so here are some more, I would say, derivations or explanations, right? So basically, you just set this drag force with the electrostatic force, right? So electric mobility is just QC divided by 3 pi mu dP. And further, as we introduced earlier, the C here is the Cunningham slip correction factor, right? It's a function of the Newton number, and C when the let's say that when the particle size is larger, it's constant. When the particle size is smaller, then C is proportional to 1 over dP. Okay, when in free molecular regime. Okay. So here it's further plotting some more relationship between the electrical mobility and particle size. Okay, so if you recall for this equation here, the electrical mobility is inversely proportional to particle size. And also here you have this C factor here. So basically this means that if you have a larger particle, its mobility, its electrical mobility is going to decrease. This also makes sense, right? So larger objects are less mobile compared to the smaller objects. Larger particles are less mobile compared to the smaller particles. Okay, so because of that, if you plot this relationship between the electrical mobility and particle size in the log scale, right, you can see this decreasing trend, right? And further, you could notice that in different regimes for different particle sizes, there is a different slope. So now if I ask you again, what is the slope here? So in terms of this section, in the free molecular regime, what's the slope? It's going to be -2, right? And then in the continuum regime, it's going to be -1. And this is because the electrical mobility, again, is proportional to C divided by dp. And we said that when in the continuum regime, when the particles are in continuum regime, C is equal to 1. In the free molecular regime, C proportional to 1 over dp. That's why you have a -2 slope here. Okay, so here you can also see that we could have different lines representing different number of charges onto the particle. As we said, when we neutralize the aerosols, they can be in with different charging states, right? If they have different charges, then they could have different electrical mobilities. That is reflected over here, right? And NEC. Okay, so because of the different number of charges, so you can see for the same particle size, if you have double charge, then their mobility, electrical mobility will be higher, right? Because their velocity will be higher and they can go all the way up, right? So if it's 5, right? So it's even higher. So this also means that when we are trying to collect particles, basically set up certain velocity, set up certain electrical mobility on our DMA, we could collect particles of different sizes, right? For example, if you're trying to collect particles of 100 nanometer. So what the DMA will do is it will select certain mobility, and because of that, you can collect, let's say 200 nanometer, okay? You will be able to collect particles of around 300 nanometer, that's carrying 2 charges. You can collect particles of 300 nanometer carrying 3 charges, and so on, right? So it's a mixture of particles with different sizes and different charges. So what that means is that for the CPC measurement you conducted here, it's more complicated than a uniform size. Okay, so we talked about how we can convert the electrical mobility to particle size. What about from voltage to electrical mobility? How do we do that conversion? Because we're controlling the voltage and we assume that we're selecting certain particle size, right? So how do we do this conversion here? So on that, there have been some analysis, and I would say that I recommend you to read this Newson and Whitby paper by 1975. So here I also have the, let's say, the title page of this paper. It's over, let me see. Oh, it's over here, right? I would say this is what I would call the Bible of the SMPS system, right? So Newson and Whitby made this derivation look so easy, or I wouldn't say so easy, but straightforward by making some assumptions onto the working principles of the DMA. And then we could get a very straightforward relationship, or get a very straightforward of the, let's say, the working principles on the DMA system. Okay, so now let's try to do the conversion from voltage to mobility in a simple way. Okay, so now let's assume that we have particles being introduced from the inlet of the DMA. So this is another assumption to the DMA system. This is just because if you remember, for the DMA system, the inlet was like this, right? Was on the side, and then the aerosols are being introduced horizontally. So here, this assumption is made that we assume that the aerosols are being introduced from the side of the SMPS system. Actually, if you further read some papers or get better understanding of the DMA system, you can see that this assumption also works because it's assuming, in terms of, let's say, in the domain of the stream function, let's say we just consider the flow of the aerosols and sheath flow, you could make this assumption. And in simulation, let's say, by having an inlet of the on the side or having an inlet that's inside this concentric cylinder, they are equivalent. Okay. But right now, let's just assume that the aerosols are being introduced from the side of the two concentric cylinders, right? And then we could assume that some particles have the perfect size or the perfect mobility that they can be introduced from the center of the inlet here and exit from the center of the outlet here. Okay, so basically they will have a vertical velocity that's caused by the sheath flow and a horizontal velocity that's caused by the electrostatic force. So how do we build the relationship between the voltage versus the electrical mobility, right? So one thing we can do is that we can first set up this derivative, okay? So let's try to calculate this dr over dx. So dr means how far the particles travel in the radial direction. Dx is how far the particle travel in the vertical direction or along this flow direction. So basically, you can first add a dt term, dr over dt, divide by dx over dt. Okay, so dr over dt, that's basically the velocity of the particle in the horizontal direction, right? Dx over dt, that's the velocity of particle in the vertical direction. So basically this is Vr, right? Let's name this as V horizontal, or let's just call it as U. And then since the particles, as the particles are moving, this vertical velocity is also changing, right? In the center, the vertical velocity is highest. At the side, the vertical velocity is lowest. So we can just call it as UR. Okay? And this velocity is also the same, right? So no matter which direction you are at, the flow profile is the same. So it's not a function of the x. Okay? So further, for the VR, we said that the VR is the velocity, right? And further, it can be represented as z multiplied by e, because remember, the electrical mobility is the velocity normalized by the field strings, right? So you just have the z multiplied by e divided by ur. And further, this e here, which is the field strength. So when we assume that the inner electrode carries certain high voltage, let's say this is high voltage, and outer electrode is grounded, right? There is a, I would say, a field strength or electrostatic, let's say, electric field that's being built across these two concentric cylinders. So this field here, if you know the voltage that's being applied onto these two cylinders, this voltage can get directly solved by solving let's say by solving the potential that's built upon this two equation. Okay, so basically you can find out that the electrostatic field strength can be calculated by V divided by R log R2 over R1. So you could solve this field strength by using the Maxwell's equation. Okay, so I will just skip this, but I think in your undergrad classes, there are materials talking about how do you solve the field strength basically within or between two concentric cylinders. Okay, so this is the field strength. So basically, you can see it's dependent on the voltage being applied onto the DMA here, and then it depends on the R. Basically, the R is how far it is from the axis of these two cylinders, right? So if it's closer to the axis, then you will have a stronger field strength, and this makes sense, right? So when the R, or I would say when the inner cylinder goes to very thin, right? When you just have a wire here, then you will ionize the air in this space, right? You get corona discharge. So that's why that's because the field strength is too large. But coming back to these two concentric cylinders, or the DMA here, right? So it's a function of the R here. When the distance, when the particles is away from the center electrode, then the field strength is smaller, right? When the particle is closer to the center electrode, the field strength is faster. And then it's also dependent on the R1 and R2, which is basically the diameter of the inner electrode and then the diameter of the outer electrode, right? Or the inner diameter of the outer electrode. Okay, so because of that, you could plug it in. So you have Z multiplied by V divided by R log R2 over R1 UR. Okay, so now let's just consider the particles that can make this perfect run. So from the center of the aerosol inlet to the center of the aerosol outlet, right? So let's just consider we have this perfect size that goes through along this trajectory. So we could rearrange this equation here. So we could have basically R and UR. So you could have R, UR, dr equals ZV divided by log R2 over R1 multiplied by dx. Okay, so if we're just talking about this perfect size here, then Z and V are just constants. They're not a function of X or R, right? And then R2 and R1 are constants too. So basically, this is a constant. And then the R is always changing. So now what we can do is we can multiply 2 pi on both sides and then do an integration. So integration is from R1 to R2. Okay, so now if you look at the term on the left-hand side, so you have 2 pi R, which is a circumference of some of any location, right, of the R location. So you have the circumference here. Circumference, right? And then you also have dr. Dr is basically the tiny section that we're trying to integrate, right? Dr. And also you have ur. Ur is the velocity that's going through this tiny direction. So when you integrate it from the R1 to R2, basically this is just calculating the flow rate, right? This is a flux of the flow going through dr, and then you're deriving that between R1 and R2. Okay, so now if you consider R1 and R2, so we're using R1 and R2 directly as the radius, but actually for this perfect trajectory, you need to consider the flow rate from here to the flow rate from here, right? So basically, it's the flow rate between these two locations. What's the flow rate that's going through these two locations? Okay, so you could calculate that. Basically, that is just the Q sheath flow, right? It's the sheath flow here, plus half of the aerosol flow, and then minus half of the sample flow, right? This is the flow rate. And then on the right-hand side, you just have 2 pi ZV divided by log R2 over R1 dx. And then for the dx, if you're integrating from like along this trajectory here, then you will just have L over here. Further, we could do some derivations of the QA and QS, right? So remember, QA plus Q sheath equals QS plus QE, right? So then you have QA minus QS just equals QE minus Q sheath. And then you have this 1 over 2 term here, which is giving you 1 over 2 Q sheath plus QE equals 2 pi ZV divided by log R2, R1 multiplied by L. So now you could have Z equals what? Q sheath plus QE multiplied by log R2 over R1, and then you divide that by 4 pi VL. Okay, so this is the relationship between the electrical mobility and the voltage. All right, so you can basically it's a function of the working condition for the DMA system, and you derive that just by doing this integration of the along the particle trajectory, right? So then by looking at this equation, you can find that the higher the voltage, right? When you use a higher voltage, then you will have a smaller mobility, right? The smaller mobility means that the particle size will also be the highest. So when you're scanning the voltage, that's added onto the, let's say that's added onto the SMPS, right? When you're scanning it up, let's say it's time and then the voltage, right? When you're scanning the voltage, then the particle size will also get scanned up, right? So you scan from the, if it's an up scan, then you start from the smallest size to the largest size. And commonly for these SMPS system, you have the largest voltage of 10,000 volts. Because if the voltage is further higher, then it's going to ionize the air that's surrounding the inner electrode. So you have a breakdown of the air here because the voltage is too high, right? You'll have the coronal discharge or sparks in this DMA system. Okay, so basically this is how we relate the, let's say, the voltage to the electrical mobility, and we further said the electrical mobility can be related to particle size. So now we have this one-to-one correspondence between the DMA voltage and the particle size. Let's say if you set it to be 1000 volt, then you will be able to find out what is the size of the particle that's being selected. But one thing we need to keep in mind is that we are assuming the particles carrying, for this size, we assume that the particles carry one charge. Actually, you can also find out what is the size of the particle carrying two charges, right? You will do that conversion when you're trying to convert the voltage to particle size, okay? You can also find out what is the size for particles carrying three charges and so on. Okay, so this is how we convert the voltage to particle size. And then in terms of converting the CPC reading to the number concentration, it is going to be a little bit more complicated, right? So we mentioned that the particles can carry multiple charges, which means that the concentration that we receive downstream of the aerosol outlet is going to be particles of different sizes with different charges. Now let's just start with a simple scenario again. Let's assume that the selected particles carry one charge only. If they carry one charge only, then does it mean that the aerosols we collect from the downstream are all of the same size? Right, so we mentioned that the ideal situation is that particles carry the perfect size that it will enter from the center of the aerosol inlet and exit from the aerosol outlet, right, the middle of the aerosol outlet. But are there other sized particles getting selected? There will be, right? So let's assume, for example, if we're still talking about this perfect size, then if we move around this inlet, right, because the aerosols are not only being introduced from the center. So then particles nearby this inlet, at the center of the inlet, can also follow a similar trajectory and further get collected. And if you go to extreme, let's say the particles near the wall, they can also go through this trajectory and get collected. Okay, the same thing on the right side of the wall, they'll get collected. But then for particles of a different mobility, they may be selected as well. So now let's assume that some particles carry a different size and then they have this trajectory that's further upstream of this inlet here, right? You can see it's upstream of the inlet. So if I may ask you a question, is this size larger or smaller compared to this perfect size? Right? So they're going to be smaller, right? So particles of smaller sizes will move faster in the horizontal direction, which means that they can collide onto the inner electrode at an earlier time, right? So basically, it's going to be the upstream of this aerosol outlet. So you can see that there will be scenario that for the smaller particles, they will also follow certain trajectory and then get collected through the aerosol outlet. So we're talking about aerosols with sizes, let's say, between this range, okay, that can follow trajectory between this range. So a little bit smaller particles can still go through, right? They can still enter this aerosol outlet, right? And then when the particles are further smaller, let's say their trajectory go along this way, then they will not get collected anymore. They will just get collected onto the center electrode and stay right there, right? So this means that there is going to be some particles, smaller particles, getting collected when you set the DMA at certain voltage, okay? And then for the larger particles, it's the same. Some larger particles, they can exit from the right side wall of the inlet and then enter from the left side wall of the outlet, right? So larger particles can also get collected. So because of that, people define this function called the transfer function of the DMA. So the transfer function, people use the omega as the term. So the transfer function is the probability that a particle of mobility Zp will be transmitted from the aerosol flow to the monodispersed sample flow. Okay, so basically this is the probability function that particles of any mobility that can get selected. So if you think about what we have shown already, right? So if we plot the Zp, if the particles have the perfect mobility, right? The perfect mobility, then they're definitely going to get collected, right? So they're going to have a 100% collection efficiency. So then what happens to the smaller mobility or larger mobility particles? How are they going to change? So we know that for the very small particles, there is a certain value, that certain mobility that they can still get collected, and after that, they're just zero. And then smaller mobility means larger particles, right? And then also, similarly for the larger mobility or smaller particles, there is a specific size or is a specific mobility that above certain range is all zero. What about in between? Okay, so again, I'm just asking you to refer to this Newson and Whitby paper. So basically, the transfer function of the DMA is going to have a triangular shape. Okay, so there's going to be a linear decrease of the probability, or I would say, a linear decrease of a probability as a function of the mobility. Okay, so there are more derivation over there, and if you're interested in these, how the DMA works, feel free to go over that. Okay, so basically you can plot this probability function as a function of the electrical mobility, right? So this means that when we're using DMA to classify particles or set up certain voltage onto the DMA, there's always going to be particles of different sizes getting collected, right? So we're trying to set up, let's say, collected 100 nanometer particles, then the CPC is actually collecting 99 nanometer and 100 nanometer particles. And people further defined this transfer function. For example, if you want to reduce this missampling of the particles with different sizes, right? What should we do? We should make this transfer function narrower, right? So the ideal situation is that we can make it a straight line. But that is going to be very challenging to do, right? So I'll show that later on. So basically, the resolution of this, or the width of this transfer function is going to determine how accurate our DMA is in collecting particles of different sizes, right? So because of that, people define this width term as the full width at half maximum. Right? And further define the resolution of the DMA as the centroid mobility, Zp star, divided by the full width at half maximum. And you could also check this paper here. So people find out that the resolution is just Q sheath plus QE divided by QA plus QS. Okay, it's the flow rate. It's the ratio of two flow rates. So remember, This is a sheath inlet, this is sheath outlet, this is aerosol inlet, this is aerosol outlet. And for the SMPS system that we showed earlier, which uses a recirculation of the sheath flow, it has Q sheath equals QE, right? Which also means that QA, since QA plus Q sheath equals QS plus QE, right? So this means that QA also equals S, QS, right? Which means that for the SMPS system we showed earlier, is going to just have a resolution of Q sheath flow divided by QA. So for the common SMPS systems that we use, we normally use a sheath flow of 10 liter per minute and aerosol flow of 1 liter per minute, right? Which means that the resolution for the transfer function is going to be 10. Okay? So this is how people derive the relationship between the voltage to the particle size, and also trying to see what the CPC reading really means, right? We thought that the CPC is just reading particles of the same mobility or even same size, but it's not. It's reading a mixture of particles with different sizes, and this mixture is dependent on how you operate the SMPS system. Okay, so this is how people represent the transfer function. So as we have shown here, we could show the transfer function as a function of ZP, but there's also more easier ways that you can just divide ZP by the centroid or this perfect mobility, right? So this perfect mobility also depends on, or this GP star also depends on what size of the particles you're talking about. For example, you're collecting 10 nanometer particle, collecting 100 nanometer particle, or 200 nanometer particle. These centroid or this perfect mobility are also different, right? But based on the derivation we have right now, so this relationship or this transfer function shape is not dependent on the particle size. So all of the, no matter what particle size you are talking about, is independent of particle size. Okay, so this is so the reason why we have this shape, this same shape of the transfer function is because we have the assumption that the particles are not diffusing. We're going to talk about the diffusing particles in next few slides. Okay, so then we said that for the SMPS system that we showed earlier, it assumed that the Q sheath equals Q axis, right? So what if the Q sheath is not equal to Q axis, right? So basically you can have, let's say, more sample flow compared to more aerosol flow, right? So if you draw that in this system here, they will represent, let's say, a wider aerosol outlet, right? So now if you think about this scenario here, so basically the extreme that is that you have particles that enter from here, right? This is the smallest particle, but then the particles can have the same or the maximum collection efficiency at different mobility sizes in between, because now you made the aerosol outlet wider, right? And then the more extreme is that for the very large particles, then they will follow this line here. So if you plot the transfer function, they're going to have a trapezoidal shape, right? And you also have always have 100% for certain ranges. And the same thing could happen when you have narrower outlet. So when you have a narrower outlet, then you have the outlet that looks like this, right? So you have the extreme that the particles of the smallest size can get collected here. And then for particles, even for the particles of the perfect size, right, only a fraction of them can get collected, because not all of them can enter from this tiny slit here. Okay, so because of that, you will also have a trapezoidal I would say the transfer function, right? And then now the thing is that the maximum transfer function or the probability is not going to be 100%. It's going to be below 100%, because not all the particles of this perfect size can get collected, right? So just to summarize these non-ideal condition or these different flow rate condition, so Mark Stosenberg from University of Minnesota published his PhD thesis trying to summarize how the non-diffusing transfer function is dependent on this normalized electrical mobility. And you can see that indeed, under certain condition, you could have this ideal triangular shaped transfer function, but most of the time they're just going to be trapezoidal, right? And it's dependent on certain parameters. For example, the delta term here and beta term here. So the beta is just the flow ratio again. It's QA plus QS divided by Q sheath flow plus Q excess flow, right? It's the aerosol flow divided by the sheath flow. And you can see earlier the resolution is just 1 over beta, right? And then delta here is the caused by the difference in the flow rate of the aerosol flow, aerosol inflow, and then the aerosol outflow. When the delta is equal to 0, which means that these two are equal to each other, then you will have a 100% efficiency, right? And also when delta, you can see that when delta is larger than 1, you will also have larger than 0, you also have 100% efficiency. And for delta larger than 0 case, that means Q sample flow is larger than Q aerosol flow, right? Q sample flow larger than Q aerosol flow, that corresponds to the scenario where you have a wider aerosol outlet, right? This is what we explained earlier in this section. Okay, so this is a nice combination of different flow conditions, and then to consider how the transfer function looks like. So from this analysis, we know that even we're operating the SMPS under a well-regulated condition, the CPC is not reading monodispersed particle concentration. On the one hand, it's because particles of different sizes can get selected, right, due to the transfer function. On the other hand, there's also the effect of the particle charging, right? So we said that particles of doubly charged or triply charged particles of larger sizes, they can have the same electrical mobility and get collected. So next class, we're going to talk about how the transfer function is dependent on the, let's say, first the Brownian motion, Brownian diffusion, and also to study how to convert the CPC reading to the size distribution. Okay, so that's it for this class, and feel free to let me know if you have any questions.